The next type of ionization source we're going to look at is chemical ionization. And I've left the drawing of electron ionization up, so if you haven't watched that video yet where I walk through the sketch of the electron ionization source, you might want to go back and revisit that. Now, chemical ionization uses the same setup. The only difference is that we're going to add a high concentration of methane gas. So instead of being under vacuum, we're going to add a high concentration of methane gas to our chamber. Okay, so now as we have this electron beam going on, we also have a whole lot of methane molecules floating around in the same area. So what does this do for the process of how our molecule is going to interact with that electron beam? Now, it could still interact with the electron beam directly, but we already said that's really inefficient, and with so many methane gas molecules around, the chances are more likely that that electron is going to interact with the methane, not with our analyte. So now what we have is our methane, and so we get methane gas plus the electron, that high energy electron. And what happens with this, okay? Well, the exact mechanisms aren't really clear, but what we do know is that this is going to undergo a series of energetic reactions and where we don't have a free electron just to pull off our ions, so we're going to end up pulling electrons off, and we might get CH4 plus, we might get CH3 plus, okay, that might have a radical, and what happens there is we get further reactions, okay, that involve proton transfer or hydride transfer, and we're ultimately going to put and generate an M plus H ion. Okay, so these could react with our molecule, and we're going to largely generate what we call an M plus H adduct. An adduct simply means that we've taken the molecule and we've added another atom onto it, and that's what's affecting the charge. So we've added an H plus on there. When we write this, we write it M plus our adduct, and we put it in brackets with the overall charge state on the exterior. Okay. Now, what does this mean about our final molecule that we see on our mass spectrum? Well, in the process of all of the reactions that lead to these intermediates that then react with the molecule of interest, there's a lot of energy losses along the way. And so when we make this final adduct, this is particularly stable and not going to fragment. This means that whereas up here we would see lots of fragmentation, this ion here is going to oftentimes fall apart. We may not see the intact ion. Here we will see the intact adduct all the time, and we may not actually see any fragmentation. In fact, it's very unlikely to give any fragmentation at all. We would call this type of method a soft ionization. So we're getting no fragmentation with the ionization. So in one case, in hard ionizations like electron ionization, we're going to see fragments. In chemical ionization, we do soft ionization. We're not going to get fragments. And because EI and CI both use the same setup, we're simply looking at or simply adding methane gas to the chamber for chemical ionization. It's really common to get instruments that can operate as both EI and CI instruments without having to purchase separate ionization sources. So you could perform both soft ionization and hard ionization at the same time. This is perhaps one of the reasons why EI and CI are so common, is especially because these are usually not as expensive instruments and they're a little bit more robust. Now in our lab we have an EI mass spectrum. We do not have it set up to do CI, though that could be a possibility at some point in the future.